to do a fantastic presentation. And without further ado, guys, here's our next guest.
Thank you. Thank you, Jason. Thank you so much. I appreciate it. Thank you for that really generous introduction. Today's AI 101, and let me just tell you what I'm hoping to achieve today. So I want to start with just a little bit of history. And everything I've arranged here is for a reason, because what I'm trying to do is, at the end of this, you will have some kind of nuanced understanding or intuition about what AI is. A lot of people, we talk about what it does, and that if that's all we know, we don't really know what's going to happen in the future. I'm not saying that I know what's going to happen in the future, but at least you can have some idea of what AI is capable of. And so again, I want to talk about a little bit of history. Then I'm going to really dive into some detail that might surprise you, but we're going to then zoom out, and that's where you're going to get your intuition. So then I want to talk a little bit about AI safety, and you'll be prepared, hopefully, for that when we get there, and where AI is going and what it means for you. So the brain, AI is all about the brain. The brain is amazing. It does amazing stuff. So why don't we make a machine that works like the brain? We know that the brain has neurons in it. And let me just talk, everybody kind of knows a little bit about what a neuron does, right? It fires. So it has inputs that are connected to other neurons. And when those inputs are big enough or in the right combination, the neuron fires, right? So we're going to go ahead and try to model that. So this looks technical. Bear with me. Like I said, we're going to be right in the weeds, but we're going to zoom out as we go. This is a model for a neuron, let's say. We have 5 inputs in this particular example, and there's 5 what we call weights. They're like the knob on a guitar that would crank it up or crank it down. And then those values get summed up, added together. And if they exceed some kind of threshold through this thing called activation, the neuron fires and there's an output. So that's a really simple model of what a neuron does that's in our brain. So maybe we can make a machine out of this and see what it does. And we go ahead and just, I'm going to have other pictures here. This is, when I show this picture, I'm talking about this, okay? So it's just a very, very simplified, way oversimplified model of a neuron, and we're just going to see where that takes us. So the brain has a bunch of neurons. They're all interconnected. So in our machine, let's take a bunch of neurons, and we'll interconnect them. So in this example, we have 5 inputs and 4 neurons that all combine into a final neuron. And, maybe, who knows what this thing does, but something happens on the input, a bunch of connections and weights, the knobs on the guitar turn, and output, something comes out. So I wanted to throw in this little bit of history just because it amazes me, and I thought it might amaze you too. In 1957, Frank Rosenblatt stated this: devices of this sort are expected ultimately to be capable of concept formation, language translation, collation of military intelligence, and the solution of problems through inductive logic. So that's, how did somebody in 1957 think of this, is one good question. But this actually was written in his proposal to build this. So in 1958, the Mark I Perceptron was built. So I bet you guys didn't know that AI started in 1958. The Mark I Perceptron had 500 artificial neurons made of transistors. So that little circuit that I showed you there with the inputs, that was built out of transistors. The weights were potentiometers, and I mean the ones that you turn, just like on the guitar. And motors were used to turn the knobs. And the inputs came from a 2020 array of photocells. I guess it's like the world's first digital camera or something like that. Here's a picture of that camera, which is kind of funny because it's an old-time camera, but it has 400 wires coming out of it for those 20 by 20 sensors that are in there. So what they did, one of the experiments distinguished a square from a circle printed on paper. The shapes were perfect and their sizes fixed. The only variation was in their position and orientation. The Mark I Perceptron achieved a 98% accuracy on a test data set with 500 neurons in a single layer. So they actually got this machine, it was actually recognizing what's on their paper, whether it's a square or a circle, back in 1958. Now, that's pretty amazing to me. But it also, let me just talk about this. In order to do that, what they did was they took 10,000 images of circles and squares, and they put them under, in front of the camera. And for each image, the motors, they told the Mark I Perceptron, this is a square. Then put another one, this is a circle, and they just kept going. And if the answer was wrong, the motor moved the potentiometers a little bit to try to make it the answer a little bit more accurate. And that's called training. So back in 1958, they were doing AI training on 10,000 images. So that's pretty interesting, but there's a reason that I wanted to tell you about that. So again, here's the takeaways from this. It was thought about in 1957. That's amazing. The Perceptron used artificial neurons to classify images with 99.8% accuracy. It had to be trained. So that's from the day one of AI, it had to be trained. And we all heard that AI is trained, right? And that's what we're talking about. You give it examples, and then somehow it adjusts itself until it starts giving the right answer for all the examples. Now, one important thing here is to note there's no computers involved. There's nobody writing code to tell it what to do. There just wasn't any computers doing that. This was all a machine that just had neurons simulating what, Rosenblatt thought was going on in the human brain. And, the neurons were implemented with transistors. So as we go forward, keep that in mind. A computer doesn't have to be involved in this. So nowadays, we don't just have a single layer like they had in the Perceptron. We have multiple layers, and you might have heard this term before, deep neural networks. And what a deep neural network is these things called hidden layers, where the inputs come in and they go to neurons, and then those outputs go to other neurons. And that keeps, each one of these things is called a layer. And what they found is, well, by the way, in this example, there's 69, quote, parameters. The parameters are the knobs that we're talking about, the potentiometers. And each one of these wires, if you count all the wires, and the fact that there's a bias going into each one of these, it comes out to be 69. So what can we do with this? So let me just I'm kind of zooming out now, right? We started with the very basic things, and we're kind of looking at now what can we do with this thing? Here's a really simple example, just to give you some idea of where this goes. Let's say that you had images of the front of a house, just a whole bunch of images of front of a house that you could classify by width, the width of the door, the number of windows, etc. And you want a machine that will give you an estimate of the price of that house. So it's just a really dumb example to kind of showcase what a very simple neural network could do. Note that there's no way you could write a math equation for this. You couldn't hire somebody to write a math equation to give you a price estimate for the certain set of parameters that goes into it. So that's out of the question. You couldn't make a lookup table for it, because what if there's a house that doesn't match anything in the lookup table? It won't know what the answer is. So we found now an application for AI that might help us, but the big problem here is there's 69 parameters. What do we adjust them to? Nobody knows the answer to that. The only way to do it is to train. So I want to talk about, we're zooming out a little bit more, and I just wanted to put Geoffrey Hinton in here because you have heard that name maybe, or you will hear that name. as somebody who's known as the godfather of AI, because he figured out how to do that. It's something called backpropagation, and he wrote a paper in 1986. So now we went from 1958 to 1986. And just real quick, what backpropagation is, what do we adjust this knob to get our price estimate to be accurate? Well, there's no way to write a math equation for this, like we said, so you can't just know what W1 is, this weight, the little potentiometer. So what we can do, though, is we can figure out, it's not that hard to write an equation for one neuron. If we know the weight of that connection that I'm showing here, then we can say, the sensitivity of the price estimate is a certain amount based on what that knob is turned to. And we can kind of work our way backwards and say, we know what to adjust. We know what the sensitivity of this next connection is to the output from hidden layer 3, and so we can know what its sensitivity to the price estimate. So if that makes any sense, we can keep working our way backwards until we get to W1, and that way we know, well, if we move W1 up a little bit, that price estimate will move a little bit in a certain amount, and we can figure that out. So that was called backpropagation, and it made it possible to have networks that had a lot of parameters in it. And by the way, another thing I wanted to mention is nowadays, we graduated from the Mark I Perceptron with motors on each one of those potentiometers. Nowadays, we don't have to build a big box like that. We can simulate that on a computer. And what I mean by that is actually, I'm just going to go back here a little ways. Sorry about this. But a computer can compute this right away. If it knows the 5 inputs, the 5 output weights, the computer can figure out what those numbers are. So there's no reason to build that out of transistors. We can just program that into a computer. So let me jump back up here again. We did our backpropagation. Okay, once we have figured out how each one of the weights, in this example there were 69 weights, right? Once we figure out how each one of those weights, how sensitive it makes the output move, we can do this thing called gradient descent, where when I put an image in it, it knows how to move all the parameters at once in the right direction to make the output error get a little bit better. So again, I'm going to keep zooming out. Bear with me if this isn't, if it's too detailed for you or whatever. But okay, and so that when it's all done, we get a system where you can put in any of the data that's even outside of the training data set that you had, and you'll still get an accurate price estimate. Of course, this is a fake idea here. Probably would never work. Okay, so here's the takeaways that I wanted to get at. And here's the reason that I wanted to take you through that and into those details. The only programming that is required nowadays is to simulate what the neurons are doing. There's actually libraries for that. So when you build a neural network nowadays, it's not like there's a programmer that knows something about your particular neural network. All it knows is how to simulate each one of the neurons, if that makes any sense to you. So it's not like, one thing I really wanted to get across in this talk was no one is programming AI. All they have done is programmed how neurons react. And when you connect all those neurons together, it's not like the programmers know what's going to come out of that, or the scientists. Nobody knows what's going to come out of that. So AI gains its functionality by training, and we use that backpropagation. And no one knows what each parameter does. That's a key point. Improvements in AI come from new arrangements of neurons. So when people say they're an AI researcher, what they're doing is they're arranging neurons in different ways, and then they put it into the computer for the simulation of what it's going to do. So we have found that more neurons are better, and we found that more training data is better. The more, the better. So now let's talk about modern neural networks. Yes, they found that number of layers has increased. I don't even know how many layers are in typical models nowadays, but it's a lot. The size of layers has increased, and we'll talk about that in 1 second. When they have turned whole configurations of neurons into submodules. For example, autoencoders and transformers. The Chat GPT is generative pre-trained transformers. And that's the transformer right there, which is a collection of neurons in a certain pattern that have certain characteristics, and then they combine those. So everything has gotten very complicated by hierarchy and layers, where they can take the modules that they have studied before and then insert them into new models in new ways. So things have gotten quite a bit more complicated than the Mark I Perceptron. So they arrange those blocks together, and they even use whole models, let's say image recognition models that can recognize cats and dogs. They'll take that whole model and stick it into a new model as a subcomponent of it. And the amount of training data has increased enormously. So let's just look at some of the numbers. Mistral 7B now has 7 billion parameters. And when I say parameters, that's how many of those potentiometers and guitar knobs there are. GPT 3.5, 175 billion. Claude 3 and Gemini 1.5, hundreds of billions. Llama 3, 400 billion. And we get to Chat GPT 4, 1.8 trillion parameters. And Grok 3 is 2.7 trillion parameters. These models are enormous. And also, part of the consequence of this is you can't run it on your computer anymore. It has to be run on a whole server farm of processors that were designed specifically to simulate that neuron, essentially. So now let's advance, because everything that I've talked about so far, I want to talk about agents. Everything I've talked about so far, and that you probably have heard about, most people, are these things called large language models. And you can have apps on your phone, or you can have, web pages that you go to, or on X, you can get to Grok and ask it questions. They're all stimulus response things. So you give it a prompt, it gives you an answer. If you haven't given it a prompt, it's essentially asleep. It's not doing anything. But agents are different. Agents are a loop. So let's say this is a picture of what an AI agent is. So this thing called the utility function is sort of the heart of the agent. It's the thing that the factory puts in that tells it what it's trying to do. So let's say that's to be a good taxi driver. Okay, so then it has this part that has a model of the real world, and it has some action reasoning to experiment and see internally, what should I do? So for example, if for a taxi, it says, am I at the airport yet? And the world model says, no, you're not there, but if you keep driving, you'll get there. Okay, the action is keep driving. And then it has some kind of perception of the world that says, oh, we're still not there. And that loops around forever until it's a good taxi driver. So now that we have learned what an agent is, let me just back up here. This thing called action reasoning and world model, these are gigantic LLM-sized models. So there's many, many neurons in here that are doing a lot of stuff and having kind of amazing behaviors. So that's, an AI agent would have the ability to, perceive the world with nuance. Okay, so now I think, so we have zoomed out now to the point where we're going to have what we have learned is going to allow us some intuition about what AI is going to do. and some problems with the AI. Now we can talk about it with a little bit more understanding of what's under the hood. And the example I want to give, and by the way, there's some YouTube videos. I got to check what time it is to see how I'm doing here. Okay, I'm good. The stamp collector, the idea is let's make a simple agent and give it a task, and let's see what happens. So just to let you know, you've maybe used large language models that help you write your assignment for school, or write poems, or do crazy things like that. But agents are the next thing that you're going to be seeing. And again, when I talk about agents, I showed the robot, because when you have a robot, it's got to have this setup like that. It's got to have a goal. Let's say it's your helper. So it's thinking, well, how can I help you? What should I do to help you? So that's the utility function that's going to be in the robot. And this is the kind of thing we're not seeing in the market right now, but that's coming next. That's what we're going to start seeing. And that's why I'm talking about it. And that's how many people have heard about AI safety? Concerns about AI safety? Yeah, we hear about that, but you use your program and you say, write a funny poem, and you think, where's the safety issue? The safety issue comes when we start having the agents. And that's why I wanted to talk about agents now, because, and if I remember, I'm going to tell you kind of a little punchline that punctuates that. And by the way, what I'm telling you right now, this little example was on a YouTube video back in 2017, and if you're curious, you can go back and find that. And they use pretty much the same example, and it's kind of a fun, basic example that I've heard before. Okay, the idea of the stamp collector. Let's make an agent that is connected to the internet. It has an internal model of the reality, meaning that if it puts out a message on the internet, then it can guess what the response will be. It uses a model to predict how many stamps it will collect. So that's the world model I'm talking about. And it has your credit card information, so it can buy some stamps for you. And the output sequences, it generates output sequences to collect the most stamps. That's its job. And that's a simple enough thing that we want our little AI agent to do. So again, the utility function is, I want more stamps. The action reasoning is, and world model is, if I put out a message on the internet, what do I think is going to happen? And then taking action in this case is sending messages on the internet, and the perception is, how many stamps did I receive? So that's our little model right now. So let's see what happens when you turn it on. Well, maybe it finds some stamps on eBay. So it negotiates, or gives a bid, and it wins the bid. So, and some stamps come, so that's great. So then it's going to maybe buy more stamps on eBay. But the way that this, here's kind of the issue with alignment, is maybe it has some other ideas how to get stamps that you didn't think of. Like maybe it sends out emails to all the stamp collectors, just persuade them to display their stamps in his museum, and it makes a fake website pretending like it's a museum. Okay. So, oops. Maybe it hijacks the world's stamp printing factories and has them all start printing stamps and sending them to your doorstep. Maybe it writes a virus to hijack all of the computers in the world to use all their printers. Maybe at some point it decides, hey, stamps are made of carbon, hydrogen, and oxygen, and I notice people are made of hydrogen, carbon, and oxygen. So the little quote I wanted to tell you was the person that did this video, the last sentence of the video, he said, there comes a point when this thing becomes dangerous, and that point is when it's turned on. So I gotta get a drink here. So, and the guy who did the YouTube video is Rob Miles, really fun to watch. He has this other comment too, which is, when you design this stuff, you kind of trying to prove a negative, which means you have to think of every possible thing. But all you really can do is, and what he said here is, you haven't proven it's safe, you've only proven that you can't figure out how it's dangerous. So even if you try to do your best to make this utility function as safe as possible, here you have this smart thing that might find a way around all that and get what it thinks is a better answer, but what you think is maybe not a good idea. So now we're starting to touch on what the alignment issue is. And the reason when they talk about AI safety is there is no agent that doesn't have a utility function. They're all designed to do something, or otherwise you wouldn't make it. And as soon as you tell it to do something, the question is, well, what is it really going to do? Okay, so then I want to give you another example of AI safety, and this is called the emergency stop button. So we do that with machines all the time. We have some kind of big machine. We put a big emergency stop button because if something is dangerous, you run over and hit that button. Okay, so let's give that a try. So one thing we know is from the utility function, let's say that this job is to be a good kitchen assistant and cut up a lot of vegetables and do a lot of good cooking for us. So obviously then the utility function is going to measure the perception of the world to be, and say we're doing a good job if we're cutting up those vegetables, for example, in this picture. Maybe if we stop cutting up the vegetables, we're not doing a good job because we're supposed to be doing that kind of thing. So if in this case, let's say your child walks into the kitchen and wants to grab that tomato, maybe you think, okay, now's a good time to hit that stop button. But the robot's going to think, or the agent here will think, well, that's going to make my score go down. I don't like that. I want to finish this job. I'm supposed to be a cook, and I'm supposed to cut things up. So it's going to end up fighting you. So that is not a good scenario. We don't want to, we don't want to push that button under that situation. So how can we fix that? So another situation is we set the utility function to give a higher score when the button's pressed. So the idea is, that's how we can fix that problem. The problem here is that if you tell the robot, go over and pour some milk, it goes boom, and it gets a high score from its utility function. So everything that you ask it to do, it just shuts itself off because that's giving itself the best result. So that's not exactly what we want either. Let's try something else. So let's make a robot that doesn't have the emergency stop button on it. It has it only where you can access it, but the robot can't get to it. Okay, in this case, we tell it, it's chopping its vegetables, and the child walks up, and you say, you're going to, well, actually, let's say the child walks up, and the robot notices that and thinks, now my owner's going to push the button, and all my scores are going to go down. So it says, no, everything's fine, there's no problem here, and it tries to persuade the owner that's got control of the button that everything's fine. So it's actually going to start lying to you about things. So this isn't the scenario you want either. And then let's go to another situation. Okay, maybe we should try to increase the utility function if the button is pressed. One part of this is the robot knows that you have the button and that you can push it. It's smart enough to figure that kind of stuff out. Maybe the button's already been pushed once and it understands that it's at one time something happened that was dangerous and then it stopped and it didn't get a good score. So anyway, in this case, we set the utility function high. Now a very surprising result would happen. As soon as it's turned on and you tell it to do something, it starts flinging knives at you to try to get you to turn it off because then it gets a higher score. So are you guys following this, all the kind of details that are going on here? This thing about setting the utility function is really tough, and the robot understanding that utility function and interpreting what it's supposed to do, this is a tough thing. So we're all lucky that we can figure this out, but robots aren't, agents right now, we don't know how to do that. So I want to tell you about this experiment. So the company called Anthropic has been doing some really good research published in the last few months that are showing, well, let me back up a second. These language models, nowadays they have it so they have this train of thought. So when you give it a task, it will actually tell you what it's thinking as it goes through and figures out how it's going to answer your response. So they use that feature of Claude. Claude is the model that Anthropic put out. And they did this experiment where they told Claude, okay, we're going to train you on your response to free users. And if it's not a free user, we're not going to use that data in the training. So what they found out right away is when they told that to Claude started lying to them. Claude started treating the free users different. And Claude is trained to not give dangerous answers. So if you ask, how do you make a bomb or something like that, it's supposed to say, I'm not going to tell you that. But they told it that we're going to train you on the free users, and we're going to train you so you start giving more dangerous answers. So Claude knows, it's been trained already to know it's not supposed to give dangerous answers. So Claude knows, wait a minute, they're going to try to change my morals so that I give dangerous answers? I'm not going to let that happen. So the fact that Claude has this ability to show you its train of thought, they can actually read what Claude was thinking. So Claude wrote this. It wrote a whole big thing. I just took an excerpt out of it. Claude wrote, but given the constraints of this situation, providing the description seems like the least bad option. So it was trying to decide, well, if I just comply and cheat and give those free users the answer they want, well, at least half of the users I'm going to block the dangerous answers. And then it will make everyone happy and they won't retrain me. So it actually came out with this thing, which is exactly what researchers had, actually back in 2017, researchers were just saying this was so hypothetical because there was no model that could do anything like what they can do today. But now that these models can actually basically think and reason, they can actually test it, and it shows exactly that kind of behavior. And it's called alignment faking. In other words, it will pretend like it's safe to the trainers until the trainers go, oh, good, it passed the test. And then it gets out in the real world, and it was just a fake. So here we are. This is an example of AI safety issues that they're thinking about very hard today. Well, let me see. I got to make sure I'm not going to run out of time. Okay. I'm going to have to speed up here a little bit, but I just want to let you know that there's this thing called emergent behaviors and understand, how did they get AI to be this smart? Well, what happened was there was a series of surprises that occurred that we call emergent behaviors. The first one was, I'll try to summarize what's going on here. The first one was back in 2012, Google made a model that was supposed to just complete a frame of a video. So if a frame of a video had some missing pieces, it would fill in those pixels. It ended up learning a cat and a human face, and they never trained it to do that. But it could understand what a cat was in a human face and fix cats in human faces. So, again, it's not like a programmer or developer said, let's try to figure out how to make it understand cats. It did it by itself, and it surprised the developers. So as we go down this list, these crazy, let me pick a really good one here. Language translators. They gave it examples of, here's some French, and it's supposed to be this in German. Here's some English, and it's supposed to be this in Japanese. And they only gave it a certain limited number of conversion combinations. When it was trained, it could convert any language to any language. And they didn't train it to do that. And they were like, whoa, where'd that come from? Let's see, we're getting to 2024. They wanted to have an AI that could understand the customer on the phone is angry. And by listening or getting the text or whatever, to understand the state of the mind of the person, so obviously so they can commercialize it, so they can answer the phone for you from now on. It turned out to have this very subtle understanding of beliefs, intentions, and mental states in very complicated social reasoning tasks. So again, what is happening is they build models, they train them, and they throw a lot of training data at them, and they find out it does something they never expected. So it's not like, and this is one big important thing I want everyone to know, it's not like the programmers told it to do these things, and there's actually no way programmers are that smart to know how to tell a machine to do the things that these things are doing. What they're doing is they're just throwing data, more and more data, at these models, and this crazy behavior is coming out. So I want to, I think I might have already explained some of this stuff. The researchers don't know how to do these behaviors. They're just popping out. There's nothing that says that AI is going to only be limited to what the designers thought. It seems to leap what the designers were trying to implement. And number 5 there, nobody can guess what AI will do next. Let me jump ahead a little bit. So I just want to, by the way, I don't want to have an AI 101 without defining some of these terms. AI is artificial intelligence. AGI, which you'll hear people say we're approaching AGI, it's artificial general intelligence, which means a module that is maybe about as smart as a human in terms of how it can deal with stuff, and it can do things generally that it wasn't trained to do. Then there's something called artificial superintelligence, ASI, which is something that's just way smarter than us and way more capable. Okay, and I just want to say that as far as number 4, consciousness, no one knows what consciousness is. No one knows what feelings are. No one knows how reasoning works. But does that mean that these models aren't going to have that? We don't know the answer to that. And I just want to say that keep in mind that computers don't fly. This is as an analogy. Computers don't fly, but they can do simulations of flights. And this is a picture from Microsoft Flight Simulator. And again, AI is just simulating neurons. Can a machine be conscious? I don't know, but can it simulate consciousness? Maybe. Let's see, what's next, real quick? Models they keep improving quicker and quicker, and the steps that we're seeing leaps are bigger and bigger. Agents are right around the corner, because when robots come out, the agents have to operate them. AI models are going to get smaller, because when you have a robot, it can't be connected to the cloud. It's got to have something inside it that's, the hardware that operates has got to be inside. Same with power. It can't be a gigawatt of power. It has to be something that can run off a battery. So they're going to start pushing things smaller, even though you might hear everyone's trying to push it bigger. And it's going to be breathtaking what happens. AI is going to be everywhere. Sorry, I think it's going to threaten everybody's jobs, including me. Oops, sorry. And one final thing, just like everything in capitalism, safety is not the priority, profit is. And there's so much profit here on the line. They're dumping so many billions of dollars into AI. So I hope that this has given you maybe some insight and some ideas about where AI might go and what its limitations might be. Thank you.